In the previous lecture, we had discussed about the phenomena of conduction. Now, we shall be discussing about the phenomena of convection. Please note that we are simply discussing about only the basics of conduction, convection and radiation. But however, we'll be studying these topics in very detail afterwards. So, if we talk about convection, okay, it actually takes place between a surface, for example, any surface, such that the temperature of the surface is Ts and the temperature of the ambient is T infinity. T infinity actually stands for the temperature of the ambient surrounding, and Ts stands for the surface of the temperature, such that the convection heat transfer coefficient of the atmosphere or the ambient surroundings is S. Okay, for example, say this is a hot plate. Okay, so this is the hot plate. So we see that there is a upward movement of air. Now air will move upward in the upward direction, and it has been given as T surface is greater than T infinity. This has been given to us. For example, we use a fan here. Alright, so what will happen? The air which is in vicinity of this hot plate will definitely rise in the upward direction due to the decrease in its density. Okay, now if the motion of the fan is ignored, if the motion of this fan is ignored, this is known as free convection. This is known as free convection. And if this fan or the blower is also taken into account, then this is called as forced convection. This is called as forced convection. Okay, now if we remember the gas equation, that is PV equals mRT, from here we can get P is equals to rho RT. So what we get? We have P upon rho equals to RT. So if the temperature and density relation is observed, if the temperature is increased, then definitely density will be decreased, such that pressure is kept as constant. Here we are keeping pressure to be constant. Now, convection is a mode of heat transfer which generally occurs between a solid surface and the surrounding fluid. This is actually the temperature of a fluid. Now this fluid can be water, that is any liquid, or air. Okay, this can be water or air or any fluid. Fluid is actually a substance which have the tendency to flow. Okay, and it is associated, this convection is associated with the macroscopic bulk motion of the fluid transporting the thermal energy. It is associated with the macroscopic bulk motion of the fluid. We are here considering the motion of the fluid such that the heat energy is being transmitted by the this motion of the fluid. Okay, now if we talk about free convection means it is taking place by means of itself or by means of buoyancy effect, This was about the free convection. In case of free convection, we need not to have any external agency so as to promote convection. But for forced convection, we have this fan or a blower. Now, in case of free convection, the value of H, that is the convective heat transfer, is generally low, whereas in case of forced convection, the value of H is high. The value of the heat convective heat transfer coefficient is very high. Okay, now if we talk about the forced convection, then in that case also there is a motion of the fluid, but this motion of the fluid is being supported by an external agency, that is by a fan or a blower. Okay? Whereas in case of free convection heat transfer, the motion of the fluid occurs because of the buoyancy effect. Okay, because of the buoyancy effect which arises due to the decrease in density. Okay, that was a little bit of basic about convection also. Now we will study about the third mode of heat transfer, that is radiation. That is radiation. Okay, now it has been observed that all the bodies at all temperatures, they will emit thermal radiation. All bodies emit thermal radiation. All bodies, they emit thermal radiation. Okay, at all temperatures. Please note that at all temperatures, except 0 Kelvin. Except 0 Kelvin, at all temperatures, all bodies emit thermal radiation. Okay, and this 0 Kelvin is actually minus 273.15 degree centigrade. Okay. And there is one more important point to be noted, that the temperature of a body cannot be equal to 0 Kelvin. Cannot be equal to 0 Kelvin, because if the temperature, say lowest temperature equals 0 Kelvin, then if we look at Carnot efficiency, 1 minus T low upon T high, and if T low equals 0, then we have Carnot efficiency equals to, this becomes 0, it becomes 100%. So this is actually a violation of second law. This actually becomes a violation of the second law. Okay, now for example, if we take a case, say this is a vacuum chamber. And we have one high temperature plate HT, I am naming it as, and we have a low temperature plate LT. Okay, now when the plate is at a high temperature, it will give out very large amount of radiation. But the plate which is at a lower temperature, it will give out less amount of radiations. Okay, and if they are both kept in the vacuum chamber and they are left, alright, and they are left undisturbed, then what will happen? Radiations will be transferred from one plate to the other plate, and there will be a state of equilibrium reached. And radiations, these actually radiations that we are talking about, they are in the form of electromagnetic waves. These radiations travels in the form of electromagnetic waves, that is with the velocity of 3 into 10 to the power 8 meter per second, that is with the velocity of light. Okay, these radiations are traveling with the velocity of light, or we can say that these thermal radiations are a type of electromagnetic waves. Okay, one relation which is to be noted here, if the temperature is very high, then the corresponding wavelength that will be emitted will be very low. That means temperature is inversely proportional to the wavelength of emitted radiations. Alright, we see that there is an inverse relation between the temperature and the wavelength of the emitted radiation. Higher is the temperature, shorter is the wavelength. Lesser is the temperature, larger is the wavelength. And the temperature of the body is directly proportional to the amount of energy emitted. One more relation, temperature is actually directly related to the amount of energy. As the temperature is more, the amount of energy radiated will be more. Okay, and one more thing, for example, we have sun, we have the earth. Okay, sun is emitting large number of radiations, and between sun and earth we know that there is a presence of vacuum, or rather universe, we can say universe. Alright, so these radiations are traveling from the surface of the sun and they are reaching the earth's atmosphere, okay, in the form of electromagnetic waves, right? They are traveling in the form of electromagnetic waves, okay. So can we say that radiation will take place at all temperature? No. The answer is no. The reason is radiation occurs only at a condition when the temperature difference is very or sufficiently high. When the temperature difference is very large or it is very high. That means delta T should be very, very large in order to have radiation as a heat transfer. Okay, now if we compare all the three modes of heat transfer, that is conduction, convection and radiation, we will observe that in case of Q, conduction, the heat was directly proportional to T1 minus T2, that is difference of the temperatures. Now in case of Q, convection, also the heat was directly proportional to T1 minus T2. But if we compare about Q, radiation, then heat is directly proportional to T1 to the power of 4 minus T2 to the power of 4. Actually it is proportional to the fourth power of the temperature, and this is the reason why radiation generally dominates over conduction and convection. Now let us look at one example where conduction, convection and radiation, that is all three modes of heat transfer, can be observed. For example, this is a you can say a wall of a house, we can call it wall of a house, okay. Now, and this is sun. Energy is being radiated from the sun and it is entering into the wall such that inside the wall there is a conduction of heat from one face of the wall to the other face, and then from this face the heat is being convected off. This inside transfer will be called as conduction, and some heat is also given through conduction from the outside to the outside air. Some convection is given to the outside air. Okay. Now we come to the actual topic from where the subject starts, and this topic, please study it very carefully because questions are framed from mostly this part. And we will now start with laws of heat transfer. Laws of heat transfer. Now the first law that we need to study is Fourier law. Fourier law of conduction. Fourier law of conduction. Okay, now according to the Fourier law, Fourier was a scientist. He observed that the heat is directly proportional to the thermal conductivity of the material, and heat was directly proportional to the area through which the heat was flowing. Now please mind that this area is the normal area regarding the heat transfer. Regarding the heat transfer, this area always lies normal to the heat transfer. Now next we have, it was also directly proportional to the temperature difference between a body. Okay, for example, if there are two faces, one is at T1, other is at T2, so temperature difference would be T1 minus T2. Now if we combine all these three equations, we will get Q is directly proportional to Ka T1 minus T2. Okay, Q is KA T1 minus T2. Now we know that when this proportionality sign is removed, there will be a constant which will be induced here. Now, for example, if I draw the diagram of how the actually heat transfer is taking place, this is at a temperature T1, this is at a temperature T2, and this is actually how the temperature is decreasing. This is in the x direction. This is how the temperature variation is taking place. This is dx, alright, and this is dt. This is the change in the temperature over elemental distance x. Alright, so actually I'll write it as Qx. That means flow of heat along the x direction. Qx is equals to minus Ka dt over dx. Qx is equals to minus Ka dt over dx. Why I am using a minus sign? The reason why I am using a minus sign is that the heat transfer will take place in the direction of decreasing temperature. That means the temperature of T1 is definitely higher than the temperature T2, and heat transfer is taking in this direction. That means from the region of higher temperature to the region of lower temperature. Okay, negative sign indicates that as we move forward, that is, as x increases, temperature decreases. That is, in the direction of increasing x, we have a decrease in the temperature. Okay, this is the first law. Second law was the Newton's law of cooling for convection. Newton's law of cooling for convection. Now, one very basic difference between conduction and convection is that in case of convection, there is the actual movement of the particles. Alright, there is the actual movement of the particles, and they gain energy from one point and they travel to the other point, and this is how the energy is being transported from one point to the other. Whereas in case of conduction, the energy transfer we studied in the previous lecture that it is possible just by two ways. First, by the free electron transfer, and the second was by molecular lattice vibration, such that there was no movement of the particles in case of this conduction. But in case of convection, there was the actual movement of the particles from one place to the other. Okay, now Newton's law says that if this is a surface, or consider it as a hot plate, and it is exposed to the ambient such that from here we have air as a fluid which is flowing in, and the temperature of the air is T infinite or T infinity, then heat which will be convected, the heat which is lost by convection, was directly proportional to the difference between temperature of the hot plate, say it is TW, so TW minus T infinity, and it was directly proportional to area also. Okay, and it was directly proportional to area also. So if we remove this proportionality sign, we will have a constant. So Q convection equals to HA TW minus T infinity. This is actually the Newton's laws of cooling. Now in the previous derivation, we see that we have introduced a constant K, and we know what is K. K is actually the thermal conductivity. It is actually the thermal conductivity of the material. It is actually the thermal conductivity of the material, and we have discussed that thermal conductivity is actually the thermophysical property of any material. Okay, now in the convection, if we are using a fan or a blower to blow this air over the surface, then it will become forced convection. It will become forced convection, and if it is flowing by itself, then it will be free convection. Now if we compare between free convection and forced convection, then in case of free convection, the value of the convective heat transfer coefficient, that is the constant which we have obtained here, H is the convective heat transfer coefficient. So the value of H in case of free convection generally lies between 3 to 25 watt per meter square Kelvin. And in case of forced convection, the value of H generally lies between 25 to 400 watts per meter square Kelvin. Okay. Now, the maximum value of the heat transfer coefficient occurs in case of boiling heat transfer having a value of 50,000 watts per meter square Kelvin. Okay. Now the next law was Stephen-Boltzmann law of radiation. One law we have Fourier for conduction, Newton's law of cooling for convection. Now we have Stephen-Boltzmann law for radiation, and it states that according to this law, the energy which is being emitted from a surface, let it be EB, the energy which is being emitted from a surface of a black body, this is EB is the surface of a black body, is directly proportional to the fourth power of temperature. It is directly proportional to the fourth power of temperature. Now if this proportionality sign is removed, we have a constant, that is EB equals sigma times T4. EB equals sigma times T4, where EB is the amount of energy which is being radiated from the surface of a black body. T is the absolute temperature. This is the absolute temperature. This is the absolute temperature of the body, and sigma is actually the Stephen-Boltzmann constant. This is the constant, or Stephen-Boltzmann constant, having a value of 5.67 into 10 to the power minus 8 watts per meter square Kelvin to the power of 4. Sometimes the value of this constant may not be given in the paper, so you need to remember it, and also remember what is the unit of this constant. Now we have introduced a concept of black body in our discussion. Now let us quickly see what actually is a black body. Actually, a black body doesn't necessarily have a black color, so it need not to have a black color. It need not to have a black color. It may be of any color. Okay. Why it is called as black body? Because it absorbs all the radiation which is being falling on it, and it radiates or emits all the radiation which is falling on it. Okay, the absorbed energy will be immediately transformed. A black body which is absorbing the radiations, so this radiations will be used to increase the internal energy of the body, to increase the internal energy of the body. And as I have told you that it need not to be a black body, because ice and snow are also examples of black body. Alright, so a black body may be defined as a body which absorbs all the radiations which are falling on it. It actually absorbs all the radiations which are falling on it. So characteristics of a black body are perfect absorber, it absorbs all the radiations falling on it, ideal emitter, and it is diffusive in nature. So please keep in mind these three properties of the black body.